Hello, dear students. Good evening, everybody. I am your tutor, Dr. Omar Rashid, in front of you with the classes, NEET DW Foundation classes. And as you are aware that we are going on with the Kirchhoff's law, Kirchhoff's junction law, and Kirchhoff's loop law. So, yesterday we have done Kirchhoff's loop laws and junction laws, in which we have described, in which we have defined what is meant by junction law. That the sum of current is entering into the junction is equal to zero. That means the current is entering into a junction. The sum of currents entering into the junction is equal to the sum of currents leaving the junction. And then we define another law that's called loop law. That is the algebraic sum of currents in the potential differences in a closed circuit is always zero, or I can say the differences in the potentials, the sum of differences in the potentials in a closed circuit is equal to zero. So let's today apply those junction laws in order to define them, in order to understand them practically, how they are, how the junction law and the Kirchhoff's loop law and the junction law, how they are applied in a circuit in order to find the unknown currents, in order to find the unknown instances. So let's try to apply them. Okay, dear. So applications. So first, let's do one thing. Let us connect the batteries. First we will do batteries in when the batteries are connected in series combination. When the batteries are connected in series combination, how the current can be evaluated, how the current can be derived by using the loop laws, by using the Kirchhoff's law, either junction law of currents or the loop law voltages. So okay, let us first, the first case, that first we will try to connect the batteries in the series. Then in next case we will connect the batteries in parallel connection, and then we will apply the voltage law, where we will apply the loop law of voltages, and we will try to find the net current in the circuit when the batteries are connected in the series combination. And then we will, and in next case we will try to find the current when the batteries are connected in the parallel combination by using the voltage, by using the loop law of Kirchhoff. So let's first make a batteries. Let's first connect the batteries in series combination. Batteries in series combination. Okay, dear. Batteries in series combination. Batteries in series combination. Batteries in series combination. So first, I will make the battery here. Okay, dear. This is one battery. This is resistance. Another battery. So then here we will make another resistance. So this is okay. So this is battery. This is point A here. This we will take point B here. So that we will take resistance R1, that I will take resistance R2, and that I will take resistance R. Okay, so this is point A. Let's take the potential of this battery is equal to E1. For example, it is potential E1. Here we will take potential E2, for example. Okay, dear. Now, what I have to, okay, so let's assume the direction of the current is this. Okay, let us assume the current direction of current is this. So that means it will go here like here, then it will go like here. Okay, so now what I have to find, I have here in this case the batteries are connected in series, end to end they are connected. So I will apply here the loop law. I will apply the Kirchhoff's loop law, which states that the sum of potential differences in a closed circuit is equal to zero. So applying the Kirchhoff's loop law on this circuit, I will try to what is the net current flowing in this circuit. Okay, so let's applying Kirchhoff's loop law here. Okay, so what is the statement of loop law? The statement of loop law is that the algebraic sum of the potential differences along a closed circuit is equal to zero, or the sum of differences in the potentials along a closed circuit is equal to zero. That means if I will take, if I will start from here. Okay, now see, this is potential of battery E1, this is potential of battery E2, but the Kirchhoff's law states that the differences, that the algebraic sum of potential differences, or I will tell the sum of differences in the potentials, So applying loop law, I will take epsilon 1, epsilon 1. Now the potential across this resistance is R1 minus times IR1. Okay, why I have taken it negative? Because if along the, if in the direction of current, if this is the direction of current over here, if is the direction of the current, for example, so it means at that point the direction of current is opposite, so I will take it minus IR1. Then again plus epsilon 2, then I will take the potential along the resistance R2 is IR2 minus IR2, sorry, minus IR2 minus IR2 minus IR, which is equal to 0, which is equal to 0. Okay, IR1 plus epsilon 2 minus IR2. So I have simply applied the Kirchhoff's loop law. Okay, I have applied Kirchhoff's loop law. I have applied like this, like that. So epsilon 1, the potential across this battery is epsilon 1, the potential across this resistance R1 is IR1. I have assumed let the current I flows through, okay? Let the current I flows through the whole circuit. Then the potential across R1 is IR1 because of Ohm's law, and the potential across the resistance R2 is IR2, and the potential across this resistance is IR. See this? We are starting from, since we are starting from point A, if we are starting from point A and we are going along this circuit, so we are going in opposite direction of current, and we are taking this epsilon 1, and epsilon 1 is the potential of the battery, this, and the potential of battery, this is epsilon 2. So we are taking the sum of the potential differences. So sum of this is the potential difference, this is the potential difference of this battery, then this is the potential difference of this battery, then the potential difference of this battery, this potential difference across this resistance is minus IR1, and the potential difference across this resistance is IR2, and the potential difference across this IR is equal to 0. Okay, across the resistance is equal to 0. So it means epsilon 1 plus epsilon 2 is minus times IR1 plus R2 plus R equal to 0. Okay, so it means epsilon 1 plus epsilon 2 is equal to I times R1 plus R2 plus R. So it means so it means epsilon 1 plus epsilon 2 is divided by R1 plus R2 plus R is equal to I, or I can say that is I, that is the current to hold the circuit is epsilon 1 plus epsilon 2, which are the potentials of the two batteries, divided by R1 plus R2 plus R. So this is the current in the circuit, okay? So this is the current in the circuit. So what I am trying to say here, I have joined the two batteries in the series correction. Then I have applied the Kirchhoff's loop law, which states that the algebraic sum of the potential differences along the closed circuit is equal to 0. So then if the potential of this battery is epsilon 1 and the potential of this battery is epsilon 2, what is the potential across this resistance? This is IR1, because V is equal to IR because of Ohm's law. What is the potential across this resistance R2? It is IR2. And what is the potential of this across this resistance? This is IR. So the potential, so the sum of potential differences. So this is epsilon 1 plus epsilon 2 minus, because we are taking sum of potential differences. Okay, or I can say the difference, or I can say the sum in the differences of the potentials, or I can say the algebraic sum of the potential differences. Okay, so it means the total potential of batteries is E1 plus E2, and the potential across the distances is I into R1 plus R2 plus R. Then their algebraic sum, that's the potential difference, this potential minus this potential is known, can be called as sum of algebraic sum, can be called as the algebraic sum of potential difference, which is equal to 0. So while supposing we can find the current in this whole circuit. The point over here is is that I want to manifest over here how the Kirchhoff's loop law can be applied to find the current in a closed circuit, and how the Kirchhoff's loop law can be applied when the batteries are connected in series, or how the Kirchhoff's loop law can be applied when the resistances are connected in series, or how the loop law is useful when the resistances are connected in parallel, and how the current can be calculated in a circuit if the resistances are connected in parallel, if the resistances are connected in series, or if the batteries are connected in series or parallel. So here we have applied the loop law, here we have applied the Kirchhoff's loop law to calculate the current while the batteries were connected in series. Now here we will, now over here I will connect to the batteries in parallel combination. Now batteries in parallel combination, batteries in parallel combination, batteries in parallel combination, batteries in parallel combination, batteries in. So here we have to apply batteries in parallel combination. So batteries in parallel, so it is, so it is, this is the battery, this is the battery, so this is the resistance, again another battery here, another battery here, so then we have another resistance here, okay dear, okay students, this is another circuit, but over here the circuit is having the parallel combination of the batteries. This is the battery, okay, over here the potential is epsilon 1, over here the potential is epsilon 2, okay. Instead of I have taken epsilon 1 and epsilon 2, right? This is the potentials across this battery and this battery. So let's take this point O, let's take this point O, and this we will take as resistance R1, this we will take as resistance R2, and this we will take as resistance, okay. Yeah, so if the current goes here like so, the current direction will be this, then it will be like that, so it will be current I like that, okay. Yeah, it will go like that, so it will go like that, okay. So let's take this point B here, point no, let's take this point B here. So at this point the current will be divided equally, okay here. Now batteries, so again, now in this circuit the batteries are connected in the parallel. Again I will apply here the Kirchhoff's loop law. So applying Kirchhoff's loop law, applying Kirchhoff's loop law, applying Kirchhoff's loop law, applying Kirchhoff's loop law in the circuit, okay. Applying Kirchhoff's loop law in the circuit containing loop law in the circuit, applying Kirchhoff's loop law in the circuit containing epsilon 1, R1 and R, containing this one, containing epsilon 1, R1 and R, okay. So epsilon 1, R1 and R, let's apply the Kirchhoff's loop law in this one containing epsilon 1, R1 and R, okay. So that means if I will take the direction of current, this is the direction of current, so what is the potential across the resistance? This is IR, okay, this is IR plus. So we are applying the Kirchhoff's loop law in this circuit containing E1, R1 and R. Now this is the direction of current. So what is the statement of Kirchhoff's loop law? The algebraic sum of the potential differences in a circuit is equal to 0. So what is the potential across this resistance? That is IR, okay, plus times. What is the potential across this resistance IR1? That is plus IR1 minus times epsilon 1 is equal to 0. That's what is the statement of Kirchhoff's law. That is the algebraic. There's this algebraic sum of potential differences. There's the potential differences. This is one potential across the resistances, and this is potential of the battery. So that is the sum of potential differences, or I can say that sum in the differences of the potential. Sum of the differences of the potential is equal to 0. So now this is one equation, okay, one equation. Now I will apply the Kirchhoff's law on the circuit containing epsilon to r and r. Applying Kirchhoff's law, applying Kirchhoff's law, applying Kirchhoff's law containing applying Kirchhoff's law containing epsilon to r2 and r, epsilon to r2 and r. So applying Kirchhoff's law containing epsilon to r2 and r. So it means this one. So again we will take now this one. Okay, so again IR plus we are going like that. Okay, we are going like that. Okay, IR plus IR2 minus epsilon 2 is equal to 0. This is second equation. Okay, I have applied this time. I have applied the Kirchhoff's law in the circuit containing epsilon 2, battery potential epsilon 2, resistance R2 and R. Okay, so these are the two equations. So after that, here I can see here IR plus IR2 is equal to epsilon 2. So it means so from these two equations, this is one equation and this is and this is another equation. So from these two equations we can find the current in a parallel combination of the battery. So again here we can see how it is useful. This Kirchhoff's law is that if the batteries are connected in parallel, applying the Kirchhoff's law, we can calculate the current flowing in that circuit. Okay, now example of batteries. For example, I will apply more batteries. For example, I will apply more batteries in this circuit and then I will try to calculate the current. Okay, dear. So I hope you got this. This was the batteries connected to the series combination. This was the batteries connected to the parallel combination. And after that, what we did, we applied the Kirchhoff's law in circuit. We applied the Kirchhoff's law in this circuit. Then we find out how the current can be calculated in this circuit containing batteries in series connection. And then we calculated the current over here when the batteries are connected in parallel combination. Now let's do another example in which the batteries are connected in series. So for example, R2, R3. So this is R2 and then we have another battery is R3. So this is another battery R3. So up to this is epsilon n, this is Rn, this is epsilon n Rn. Okay, so epsilon 1, this is epsilon 1 R1, epsilon 2 R2, epsilon Rn. Okay, so and let's assume the current flows in that direction. So with the application of the Kirchhoff's law, let's try to find the current, how much current flows in this circuit in which n number of batteries are connected in series. Let's try to calculate the current in this circuit in which n number of batteries are connected in series. Okay, dear. So now in which n number of batteries. So now if the so this is the, let us see that current I flows in that direction. So let us go in that direction. Okay, so applying the loop law like that. Okay, so in this direction. So what is the voltage across this resistance? That is IR plus what is the resistance potential across IR, and that is IRN minus epsilon n minus epsilon n plus R2, that is R3, okay, plus IR3 plus IR3, this is epsilon 3 minus epsilon 3 minus epsilon 3 minus epsilon 3 plus IR2 plus IR2 plus IR1 IR2 plus IR3 minus epsilon 3 plus IR2 minus epsilon 2 IR2 minus epsilon 2 plus IR1, there is potential across this distance R1 is IR1 minus epsilon 1 is equal to 0. What I am writing this expression? What is this mathematical expression? This is simply Kirchhoff's loop law. That is the algebraic sum of the potential difference across this circuit along this circuit is equal to 0. What is the potential across this resistance? That is IR. What is the potential across this RN? That is IR according to Ohm's law. What is the potential difference given in this battery? That is epsilon n. So IR plus IRN minus epsilon. Why minus epsilon? Because we are taking algebraic sum of potential differences. We are taking the sum of differences in the potentials. In other words, we can say, so that is equal to 0. Okay, or yeah. So it means I can do I into R plus R1 plus R2 plus R3 plus dash Rn is equal to epsilon 1 plus epsilon 2 plus epsilon 3 up to dash epsilon n up to epsilon n divide. So it means, so after that, so current I can be given as epsilon 1 plus epsilon 2 plus epsilon 3 plus dash epsilon n divided by sum of resistors R1 plus R2 plus R3 plus dash Rn, so plus Rn. So that's how to find the current. That is how to find the current in a series combination of batteries. So that is the application of the Kirchhoff's loop law. That's when the batteries are connected in series combination. How can we calculate the current when the batteries are connected in series combination? Okay, dear, when the batteries are connected in series combination, what I have done, I have simply applied Kirchhoff's loop law, and after that I have written the statement of the Kirchhoff's loop law, and then finally I have transposed the other terms, and in this way we have calculated the current. So that's the beauty of the Kirchhoff's loop law. So that's Kirchhoff's loop law helps us to calculate the current when the resistances are connected in series. It helps us to calculate the current when the resistances are connected in parallel. The same Kirchhoff's loop law helps us to calculate the current when the batteries are connected in series or when the batteries are connected in parallel. Now, one of the important examples, okay, one of the best examples through which we can understand. So we will make another example in which we can apply both Kirchhoff's loop laws. One is the junction law as well as the loop law, so that we can better understand the Kirchhoff's loop law. In upcoming class, I will show you many problems, previous year NEET problem and DW problems which wholly and solely depend on the loop laws, okay, on the Kirchhoff's loop law. Let's do another problem over here. That's very important problem, okay, very important problem. So let me I will make a circuit over here. The circuit is, so example, this is that, so this is, okay, this right. So after that I have, this is another resistance. This is 4-volt battery here. This is 1 omega. This is 1 omega. This is 40 omega resistance here. This is 30 omega resistance here. 30 omega resistance here. This is 1 omega resistance here, and this is 80 volt battery here. This is G here. GF. this current goes in that direction, I2, the current goes in that direction. Okay, this is 20 omega resistance here, and this is point B here. So this is point H here, and this is 30 omega, and current here. Okay, so I2, and the current direction over here is this I2, and the current point is I1. Okay, dear, I1, and this is I3. Okay, see, this is one of the best examples. This is one of the most important examples, so that you can quickly understand both the laws, both the rules of the Kirchhoff's law. Junction law, here is the sum of currents entering into the junction is equal to sum of currents leaving from that direction, because over here the current I3 is entering over here and it's distributed. This current I3 is equal to I1 plus I2. So over here I will apply both the loop laws. One is junction law of currents of Kirchhoff, another one is loop law, and again then I will try to explain all of the problem. Now see what's happening here. So okay, now firstly I will write here according from the loop law, okay, from the junction law of the currents. Can I tell here I3 is equal to I1 plus I2? Yes, that is true. Why? Because of junction law. Because of junction law. Because of junction law. Okay, dear. Because of junction law. Because I3 is equal to I1 plus I2. It's because of junction law. For loop AHDCBA. Now see, I will see the loop AHDBCA. This is H, this is D, this is CBA. Where is CBA? This is point B, this is point B, this is point A, H. So that is, this is point A. Okay, I will take the loop A, H, D, A, H, D. What is C? A, H, D. With that I will take point C here. Okay, point C. A, H, D, C, B, A. Now taking the loop, taking the loop, taking the loop, taking the loop, A, H, taking the loop A, H, D, C, B, A. Okay, dear, taking the loop A, H, D, C, B, A. Now let's try to apply the Kirchhoff's loop law in this loop. Which one? A, H, D, C, B, A. Okay, A, H, D, C, B, A. Okay. So see now here, the current direction is like that. Okay, the current direction is like that. So it is going like that. So A, H, D, C, B, A. So it is minus 30 I1. Minus 30 I1. If I have taken the potential across this resistance negative, then it means the potential across this battery I have to take positive. That's the rule of the Kirchhoff's law. That's the rule of the loop law. That's the rule of the loop law of the Kirchhoff. If I am taking the potential across the resistance positive, then while applying the loop law, I have to take the potential of the battery negative. Or if I am taking the potential of the battery positive, then I have to take the potential across the resistance as negative, or vice versa. Now I am taking like that, I am going AH, so I am going like that, I am going like that. Okay, from here. So it means the current, the potential across this resistance 31 will be minus 30 I1 plus 4V plus, this is 4V plus 4V plus 4V plus 4V minus 30 I1 so plus 4V, this is plus 4V. See, this resistance and this resistance, they are in series. Okay, this resistance and this resistance are in series. So it means it will go minus times, when the resistances are in series, their net resistance equal to simply the addition of the resistances, that is 40 plus 1, that is 41 omega is equal to 0. Okay, 4V plus, this is I3, and the current entering from these resistances I3, so it will be 41 I3, is equal to 0. 21 I3 is equal to 0. Okay, so after that now I will apply the loop on this one. Now taking the loop, a at dfga, taking the loop a at dfga, taking the loop a at d, taking the loop a at d e f g a, this is e. Okay, now taking the loop a at d e f g a. Okay, this loop I am taking, this loop a, this whole loop I am taking now, whole loop a at d e f g a. Okay, a at d e f g. So I will take it now. So this is the current. Okay, this is the current. So I will take from here a at d f g a. So I will take from here. So that means it will be the potential across this resistance will be, this is 1 omega resistance, it will be let the current, and the current flowing through this resistance is I2. So it will be I2, it will be I2, but since this resistance and this resistance are in series, this resistance and this resistance are in series, so their net resistance will be 20 plus 1, that's 21. So 21 I2. 21 I2, taking the loop A at D E F G A, this loop. Okay, whole loop. 21 I2, 21 I2, 21 I2 plus now this one. Okay, now the potential across this resistance, we are going like that. Okay, we are going this 20 I1 to plus time is 30, plus time is 30 I2, plus time is 30 I1. Okay, plus 30 times I1 plus 30 times I1. Why? Because this I1 is entering from this one. Okay, okay, I will take from here. 30 I1, 30 I1 A at D E F G A. Now this resistance and this resistance, they are in series, so their total will be equal to 21 I2. Now see, since the direction of current was here and in the same direction we are going, and that's why we take 30 I1. But when we reach it here in this, the direction of current is opposite, because we are going like that, we are taking opposite to the loop, we are going like that. So here we will take minus times 21 I2, 21 I2. Okay, then plus, so then we are going like here. Okay, then it will be plus 8 dB, plus 8 dB, that is equal to 0. Okay, so these are the two, equations which we have applied. These are the two equations which we have got by using the loop law and the junction law on this circuit. Why I am saying this problem? Because this is the problem in which we have to apply both the laws of the Kirchhoff. One is the junction law of the currents, another one is the voltage, another one is the voltage law, on the loop law of the voltages. What we have done here, we have taken, this is a 30 omega resistance, this is a 4 volt battery, this is 1 omega resistance and 40 omega resistance. They two are in the series, and then we have this 20 omega and this 1 omega resistance, they are again in series, they are going from end to end. Okay, then what we have done, the first loop we took here, the first loop we have taken AHDCBA. So in AHDCBA I have taken the loop, so I have taken this minus 30 I1, for example. So if I have taken the loop, that is minus 30 I1, I have taken in the direction, in the direction of current, I have taken negative. The current direction I have taken negative, that means minus 30 I1, because I1 is the current that goes to this resistance. So it means the potential across the 30 omega resistance is IR, that is minus 31 plus 4 volt. Why it is 4 volt plus? Because we have taken potential across this resistance positive. I have taken this is negative, then it will be a positive plus 4 volt minus again the potential across this resistance. Since they are in series, it will be 41 resistance into I, so it will be minus 41 I is equal to 0. Then after that I have taken the loop A at D E F G A. So in that I have gone from this way. I am starting from this. So I1 is flowing through 30 omega resistor. It means if I have taken the positive, if I have taken the direction of current as positive, in this direction I am going, that means 30 I1, then I am going 30 I1. Over here, when I am reaching here, this resistance and this resistance, they are in series, their total resistance will be 21 omega. But over here, the direction of current is going that, and I am coming from here, so I am coming in the direction opposite to the flow of current. So over here, the potential will be taken as negative, because I am coming to the opposite direction of this potential, that it will be minus times 21 I2, and then it will be plus times 80V. So these are the two equations. I hope these are the two equations. Remember, these are the two equations. These are the two equations I have derived by applying the Kirchhoff's loop law and Kirchhoff's junction law. So actually this problem shows how the junction law and how the loop law can be applied on a circuit, so that we can calculate the currents in a circuit. So I hope that's all for today. The today class, what was the importance of today class is that we have done many problems. We have done 3 or 4 problems. We have see how the currents can be calculated when the batteries are joined in parallel. How the current can be calculated when the batteries are connected in series, and how the currents can be calculated in a circuit in which some resistors are connected in series and some resistors are connected in parallel, and in some batteries are also connected. And if we have a circuit in which some resistors are connected in series and some resistors are connected in parallel, and with some batteries are also there. So if we know the loop laws, if we know the Kirchhoff's law of junction law, and we know the loop law, we can easily calculate the currents flowing in that circuit. I hope that's all for today. Let's meet in the next class. Till then, all the best.